Welcome to my talk. I'm Zihan from University of Chicago. I will present my paper with my advisor, Chuzhoy, and Sepideh Mahabadi, both from TTIC. The title of the paper is Toward Better Approximation of Graph Crossing Number. The graph crossing number problem is a well-known problem in graph theory and graph algorithms. Its input is just a graph, and the goal is to find a drawing of the graph in the plane with minimum number of crossings. So what do we mean by a drawing of the graph? The definition is kind of straightforward. We simply draw vertices as distinct points in the plane, and we draw edges as curves connecting the point that corresponds to the endpoint of the edge in the graph. And the crossing is simply an intersection between two curves. For example, if the input graph is K4, a complete graph on 4 vertices, then this is a drawing of K4 in the plane. Its drawing contains only one crossing. So two things are forbidden in the drawing. First, we do not allow an edge to go through a vertex in the drawing. For example, if we draw this edge in this way, then it's forbidden. And second, we do not allow more than 3 curves to intersect at the same point. For example, if we draw it like this way, then this is also forbidden. So intuitively, the points and the curves in the drawing has to be in general position. And in fact, we know that K4 is actually a planar graph. So if we draw it like this, then we get a drawing with no crossings, which is also a planar drawing. So the crossing number of graph is simply the minimum number of crossings over all drawings of G. And the graph crossing number problem is to compute or approximate this number, and also to find a drawing with this many crossings. Okay, so this problem is really a classic problem in graph theory and graph algorithms, and it has a long history. So it was first introduced by Theorem in the 1940s. And since then, this problem became popular, not only because it is a natural and easy to state graph theoretic problem itself, but also because it has found a great number of connections and applications to lots of other areas. Just to mention a few: graph algorithms, visualization, VSLI design, incident geometry, etc. So graph crossing number problem has been studied extensively, according to a bibliography maintained by Virtual by 2014. So before the year 2014, there are more than 700 papers on this topic. But despite all this problem is still poorly understood from several perspectives. First, it is notoriously hard from the approximation perspective, as we will see when going over its previous work. And second, it seems that none of the standard methods, like linear programming or semi-definite programming, may work on this problem. Although there were attempts to use integer linear programming, but it turns out that they only give us some heuristics. So basically, if we want to attack this problem, we need to work from first principles. Now let's look at previous work of the graph crossing number on general graphs. So currently, there's no non-trivial approximation algorithm for the general graphs. All currently known algorithms achieve approximation factor that depends on the maximum vertex degree of the input graph. And on the other hand, the strongest hardness result is only APX hard, so really not much is known here. However, we do have one beautiful result about graph crossing number, which is the crossing number inequality. This inequality is discovered independently by Itai, Chavatal, Dearborn, Semerity, and by Layton. It says that if any graph contains n vertices and m edges, such that m is at least 4n, then its crossing number is at least of order nm cubed over n squared. So basically, this inequality tells us that if the graph is dense, then its crossing number has to be very large. So the interesting part of this problem is really when the graph is sparse. Therefore, it makes sense to look at bounded degree graphs, where the max vertex degree is bounded by a constant. And this is indeed the main direction of this research on this problem in the past 10 years. So what is previously known for bounded degree graphs? Note that any approximation factor on these slides, I'm omitting poly delta factor, where delta is the maximum degree of the graph. Okay, so when I write ON approximation, it's actually ON poly delta approximation. So the first algorithm came from the celebrated paper of Layton and Rao on multi-commutative flow and sparseness cut. They showed that we can draw a graph with n plus CRG polylog crossings, where CRG is the crossing number of a graph G, okay, which translates into an approximation algorithm of factor n polylog n. And this was improved by 2 papers that shave off some log factors. And on the other hand, the strongest hardness result is still only APX hardness. So recently, by a combination of 2 papers, first by Chuzhoy, Makarchev, and Sidiropoulos, and second one by Chuzhoy, the approximation ratio is improved to n to the 0.9. And then in a more recent work by Kobayashi and Sidiropoulos, they further improved the ratio to square root of n. In our results, it's a further improvement of the approximation ratio to something like 0.499. This might seem a little slight improvement, but we believe that the more important contribution is that our method paved the way to a better approximation. Well, just to be a little bit more specific here, all previous work with theoretical guarantee used the same framework. Okay, and this framework is proved to cannot get better than square root of n approximation. And what we did is that we introduced a new framework that breaks this barrier. Okay, so that's what we mean by pave a way towards better approximation. And eventually, by using this framework, we reduce the crossing number problem to another seemingly simpler problem called the crossing number problem with rotation system. Okay, so these are our main results. So what is this new problem, crossing number with rotation system? So the input is not only the graph G, but also for each vertex, a circular ordering of its incident edges, as shown on the right, which we call the rotation of the vertex. Okay, so for example, if the incident edges of V1 is E1, E2, E3, E4, and as shown on the right, we are also given a circular ordering of these edges, which is E1, E2, E3, E4 clockwise. And the goal is to compute a drawing of the graph with the minimum number of crossings. But the drawing has to respect the rotation at each vertex. Namely, for each vertex, the image of its incident edges must enter the vertex in the given circular order, or its flip. So is this new problem easier or harder than the original problem? On the positive sides, we know the ordering on each vertex, and this seems very useful information. On the negative side, the max vertex degree of the graph is no longer bounded. So in general, we tend to believe that it's easier, but we cannot prove it rigorously. Okay. So what's known about this new problem? Well, first, it's clear that in cubic graph, this problem is equivalent to the graph crossing number problem, and therefore it is also APX hard. Okay. And to the best of our knowledge, the only previous work studied a variant of this problem, in which the orientation of the flip of the orderings are also given. And only n to the 4th approximation is known, even in this special case. Okay. And it is easy to find a drawing with at most the number of edges squared crossings, since we can ensure that every pair of edges cross at most once, which is not very hard. And our result on this problem did a little bit better than this by pushing down the exponent 2 by 1/20. This seems a small improvement, but it already gives us a better than square root of n algorithm, approximation algorithm for the main problem, which is the crossing number problem on bounded degree graphs. Okay. And better approximation here leads to better approximation for the main problem. In particular, if we get polylogarithmic approximation here, then we can also get polylogarithmic approximation for the main problem, and which will be very great. Okay. So, okay, now I will present an overview of our algorithm. Let's first look at the old framework that all previous work with theoretical guarantee used. Okay, so this framework, it consists of 3 steps. First, we compute a planarizing set E prime. Here, by a planarizing edge set, we mean a set of edges in the graph, such that if we remove these edges, then the remaining graph becomes planar. Okay. And second, we compute a planar drawing of the remaining graph after we remove the edges of E prime. And last, we add the edges of E prime back to the drawing to get the final drawing of G. Okay. So for example, the input graph is K5, the complete graph on 5 vertices. We know that K5 is not planar, but if we remove any edge of it, then we will get a planar graph. So the planar rising edge set can simply be just any edge of the graph. And then we find this drawing of K5 minus 1 edge. And finally, we add the edge back to get a drawing of K5 with only 1 crossing. Okay. And again, all previous work with theoretical guarantee uses framework, including the paper by Chuzhoy, Makarchev, Sidiropoulos, by Chuzhoy, and 2 papers by Kobayashi and Sidiropoulos. And also, this framework is indeed the standard heuristic that is really used in practice. However, there's a barrier in the framework, so that the best approximation it may possibly lead to is square root of n approximation. And as we will show later, we propose a new framework that overcomes this barrier. So how did previous work use this framework to get algorithms? Let's look into these 3 steps in more detail. So first, it is easy to see that there exists a planarizing set of sides at most CRG, the crossing number of graph G. Because if we take the optimal join with CRG crossings, and for each crossing, we simply delete one edge, then the remaining graph is planar. Okay. And then in a paper by Kobayashi and Sidiropoulos, they showed a logarithmic approximation for computing the smallest planarizing set. So combining them together, we can efficiently find a planarizing set whose size is approximation CRG. And this is basically the best we can hope for. So the first step is basically that. So in the paper by Chuzhoy, Makarchev, and Sidiropoulos, they show that given a planarizing edge set E prime, they can efficiently compute a drawing by implementing the second and the third step in some way with side of E prime times side of E prime plus CRG crossings. Okay, so basically they compute a drawing of the graph by implementing the second and third step in the framework with this many crossings. So combined together, we can compute a drawing with at most CRG squared crossings, and this translates into a square root of n approximation of the algorithm. Okay, so this is how all the previous work use this framework and get the best, which is square root of n approximation algorithm. So, however, it turns out that this is the best approximation that this framework can give us. So as shown by Chuzhoy, Madan, and Mahabadi, for each integer k, there exists a graph G whose crossing number is k and contains a planarizing edge set E prime whose size is also k, such that any drawing of G that induces a planar drawing of G minus E prime has to contain at least k squared crossings. Okay, so therefore, if we want to obtain better approximation than square root of n, then we have to try something new because square root of n is the best that this framework can get us. So in our paper, we propose a new framework that overcomes this barrier and paves the path towards better approximation. So the new framework can be seen as a modified version of the old framework. So the first step is still to compute a planarizing edge set, which is identical to the old framework. In fact, we will be using the algorithm of Kobayashi and Sidiropoulos to implement this step and set a planarizing set of sides, approximately CRG. But then we allow ourselves to augment this set by adding additional edges to it. So we will ensure that the new edge E double prime is still small, meaning that its size is still approximately CRG. And the remaining graph G minus E double prime has some useful properties. Okay. So after this, the remaining steps are again identical to the old framework. We compute a planar drawing of the graph G minus E double prime, and then add the edges of E double prime's back. So the only change is that we do not use E prime directly, but we augment it a little bit. Okay. So does this small change help? Well, we show that it actually does. So our first main theorem shows that we can efficiently augment the set E prime obtained from the first step to E double prime, such that there exists an approximately optimal drawing of G in which only edges of E prime participate in crossings. Okay. Note that this is stronger than just saying that there exists a nearly optimal drawing of G in which the induced drawing of G minus E double prime is planar, which is equivalent to say that any crossing involves at least one edge of E double prime. And now we are requiring that every crossing involves only edges of E double prime. The one thing that is not very satisfying here is that we can only guarantee that there exists a near optimal drawing of G, but we do not know how to compute it. In fact, if we knew how to compute it, then we would directly get a polylogarithmic approximation. And it turns out that after the first step of getting an augmented set, E double prime of edges, implementing the third and the fourth step is exactly solving an instance of crossing number with rotation system. And as we have already presented before, our second main result is simply an algorithm for this problem that gets a drawing with CRG to the 2 minus epsilon crossings. So combined with main theorem 1, we get a n to the 0.5 minus epsilon approximation for crossing number on bounded degree graphs. So I should say that we did not try the best to get the approximation algorithm for main theorem 2, because at this point, the paper is already very long and technical. So the second main theorem here, we view it as a proof of the concept that we can use this framework to easily overcome the square root n barrier and get better approximation. So in the remaining time, I will focus on the proof of main theorem 1, and then I will not present the algorithm for main theorem 2 due to the limit of time. So recall that the first theorem says that there is an algorithm that, given a graph G and a planarizing edge set E prime, whose size is approximately CRG, computes an augmented set E double prime such that the size is also CRG, and there exists a drawing of G with almost optimal number of crossings, in which only the edges of E double prime participate in crossings. Okay. So the intuition comes from the previous paper by Chuzhoy. It indirectly shows that if we are given a graph G that contains a set of disjoint clusters, where the clusters just mean connected subgraphs, that satisfies these three properties, then there's a near optimal drawing of G in which the edge of these clusters don't participate in the crossings. Okay, so these three properties are three vertex connectivity property, strong planarity, and boundary well linkedness. Okay. So for example, so specifically, three vertex connectivity is basically requiring that a graph be three vertex connected, like a graph like this. So three vertex connected means removing any two vertex will not disconnect the remaining graph. Okay. The second property is called the strong planarity. It requires that the cluster is a planar graph. So if it is also a three connected graph, then it's a three connected planar graph, and it was proved that such a graph has a unique planar drawing. Okay. And the strong planarity property additionally requires that in its unique drawing, all boundary vertices, that is, the vertices incident to edges that do not belong to this cluster, lie on a single face. Okay, so for example, these blue edges are the edges that do not belong to this cluster, and the orange vertices are the boundary vertices, and they all lie on the outer face. Okay. So assume, right. Okay, so why is this intuition true? Let me try to sketch its proof very briefly. Okay. So assume this is the optimal drawing of the graph, okay, where the green edges form a cluster, namely a connected component of graph G minus E double prime. And it satisfies the three properties that we have mentioned before. Namely, it is a three vertex connected graph. It has a planar drawing with all boundary vertices lying on the outer face. Here, the boundary vertices are A and B, okay, and they are well linked inside it. So we first find a vertex C in the green part and a set of paths connecting the boundary vertices to C, which is shown on the dashed purple lines. And then we erase the green part from the drawing, and this is what remains. And we now redraw the edge of E double prime, namely the blue edges, by starting with their original curves and then extending them along the path that connects A, B to C, which is the path that we have just found. So eventually, they all ends at C. Okay. And then we place a small disk around C, and then put the unique planar drawing of the green part, which is the drawing shown on the right, back into the disk. And finally, we reconnect these blue curves to the boundary vertices A and B inside the disk like this. Okay. So this is what happens inside the disk if we take a closer look at it. So this completes an iteration of processing the green cluster of the graph G minus E double prime. So observe that after this iteration, the drawing of the green cluster is planar, and it's also disengaged from the remaining part of the graph. Therefore, if we keep processing other clusters in this way, eventually we will draw every cluster in a planar way in a small disk. And these small disks are completely disjoint from each other. So finally, only the blue edges, that is only the E double prime edges, may participate in crossings. Okay. So our plan for using this intuition to prove the main theorem 1 is the following. We start with the planarizing set E prime of edges. Recall that the size of E prime is approximately CRG. And then we augment the set E prime to E double prime, such that each connected component of G minus E double prime satisfies these properties. Okay. While we also ensure that the size of E double prime is small, which is almost CRG. Okay. So if this can be done, then the main theorem follows from the intuition theorem. Okay. So now let's follow the plan and try to get these three properties by augmenting the set E prime of edges. But first, let's start with the third property, the boundary well linkedness property. It turns out that this property is easy to achieve using known algorithms that is called well-linked decompositions. Okay. So intuitively, the well-linked decomposition starts with the graph E minus E prime, and whenever one of its clusters does not have the well-linkedness property, we decompose it into two small clusters by cutting it along some sparse cut. Okay. We repeat this process until every cluster has well-linked property. And we can show that we will not end up cutting off too many edges. In particular, we augment the set E prime by all edges that are cut off in the well-linked decomposition. Then we obtain a set E double prime whose size is within a constant factor from E prime. So let's now look at the second property, the strong planarity property. So unfortunately, it turns out that we cannot get this property while ensuring that the set E double prime is small. So consider the example shown on the right. The green circular grid is a cluster of G minus E prime that we want to ensure the strong planarity property for. The blue edges are E prime edges, and X and X prime are two other clusters of G minus E prime that are connected to the green cluster at the innermost cycle and the outermost cycle, respectively. The orange vertices are boundary vertices of the green cluster, but currently they do not lie on a single face. So how can we make them lie on a single face? The only way is to break this circular grid by deleting one edge per cycle like this. So the outer and inner face are merged into one face, and therefore the boundary vertices are lying on the same face. Okay. But the problem with this is that the circular grid may contain many cycles. So we may end up deleting too many edges to ensure this property, which we cannot afford. Okay. So the way we get around this is that instead of ensuring the strong planarity, we use a weaker property called the bridge property that only requires that the cluster has a planar drawing in which every pair of boundary vertices that is connected in G minus C lie on the same face. Okay, so now let's look at this example again. So the orange vertices are the boundary vertices. Note that if we remove the circular grid from the whole graph, then the top three boundary vertices are connected to X, so they lie on the same face. And similarly, the bottom three vertices are connected to X prime, so they also lie on the same face. But the top vertices and the bottom vertices are disconnected, okay, are not connected between each other. So they do not need to lie on the same face. Okay. So what if this bridge property does not hold? For example, there's an additional edge in this example connecting X to X prime. So now if we remove the green part, then the remaining part is connected. Okay. And we're still forced to make all orange vertices lie on the same face. But what we can show now is that in any drawing of G, the circular grid must participate in many crossings, proportional to the number of cycles that it contains. Therefore, we can't afford to remove one edge per cycle, like this. And we charge it to the number of crossings in which the green edges participate. And in fact, we can ensure the bridge property and the boundary well linkedness property simultaneously, because we can prove that the bridge property is preserved after we do well-linked decomposition. Okay, but we also have to ensure the three vertex connectivity property, and this is the most difficult part of the proof. Let me briefly explain why. So if all we want is three vertex connectivity, then we can repeatedly remove 1 and 2 separators until each cluster is reconnected. But the problem is that we cannot ensure the other two properties simultaneously because intuitively, if we remove one or two separators, then the new clusters are no longer boundary well linked. And if we then do well linked decomposition, then the new clusters are no longer 3 vertex connected. So it is not clear how this process is going to end, and even if it ends, we will end up cutting too many edges. So what we do is, again, we replace this 3 vertex connectivity property by a weaker property that requires that C is only 2 edge vertex connected, and the number of its 2 separators is small. And we can properly find a few fake edges to C and make it 3 connected. So I will not go into the details here since they are quite technical and tedious. Okay, so I will skip the summary here, and thank you for listening.